Welcome back to the series, everyone. We have been learning the Python programming language together by focusing on one particularly interesting application, machine learning. I am Gentry. I am a researcher and instructor in computer science, and this is Single Star Software, the only programming channel that is one mental break away from just posting Fortnite videos. This is the fourth video in this series, so if you're watching, you should be familiar with the core syntax of the Python 3 programming language, including how to create and use variables, how to perform operations on those variables, either arithmetic or comparison or logical. You should be familiar with how to define classes and functions. You should be able to comment your code to improve its readability and maintainability. And you should understand how to implement I/O, input-output, so printing values using print statements and getting values from your user using input statements. If those are familiar to you, great, keep on going. And if not, try jumping back to video 1 or 2, and I'll see you back here when you're done with those. In this video, we're going to be writing our first code that actually does the work of training and testing some machine learning models. Right? So last video, we learned the core concepts of machine learning. So we already know that a machine learning model is going to iteratively fit itself to some data, and after that, we'll be able to use it to make predictions about some other new data. We're going to learn today 3 non-neural models, and I hope the distinction is maybe becoming clear to you. What is a neural model or a non-neural model? So the ones we're going to look at today are the decision tree, the k-nearest neighbors algorithm, and a support vector machine, or SVM. Right? And if we're going to train these models, we're going to need some data. So we're also going to look at the UCI wine data set. So let's imagine each one of these little shapes here represents one instance of data. So we've got 3 different shapes here. So that would be 3 different classes of data, right? And they're kind of all mingled together. So from a viewpoint of information theory, we would say that this data is in a high entropy state, right? Like a bunch of blocks just laying on the ground. So our first model is going to learn to make splits in this data that's going to put them into lower entropy groups. Right? And these groups get split again and again until the model has minimized the entropy in each group. Right? Which means that they keep getting split until the model sees that making another split wouldn't decrease the amount of entropy in the group, right? So the final groups here are called leaves, and the whole structure here kind of looks now like an upside down tree, so we call it a decision tree, right? And if we drop a new piece of test data into this tree, right? So if we think about some new instance of data, it's going to get, right, compared to the rule that was used to make this split, right? And it's going to end up in one of these groups, right? And then it's going to get compared for the rule that was used to make this split, right? And it's going to end up in one of the leaves, and that's going to tell us the predicted label for our new instance of data. Okay, so now we've seen how a decision tree works. All right, so for our next model, let's look again at those same instances of data. Right, we've got a scattered plot here, a little 2-axis plot with our same 3 classes of data. So we could arbitrarily say like, oh, here's class 0, and here's class 1, and here's class 2. Right, and so when we want to drop in a new instance of data, right, a new piece of test data, it's going to have to fall somewhere on this plot. So let's say like right here. All right, so what should it be? What should the label of this new instance of data be? Well, let's think about a new strategy, right? Last time we defined a bunch of rules and split these into groups, right? New strategy, let's just think to ourselves that it should have the same label as the nearest neighbors on this plot, right? So I'm going to draw a circle around our test instance that's just big enough to capture 3 neighbors, right? And I should say I'm approximating a circle here, I guess, because that's not that perfectly round. Okay, so we're going to look at its 3 neighbors. We're going to compute the majority class. So we see that here we've captured 2 triangles and 1 circle, right? So we're going to assign this new instance of data the label 2, I think this was, red triangle, right? But what if 3 isn't the right number of values, right? Maybe we need to draw a bigger circle that's going to capture the 5 nearest neighbors, right? Or maybe the 7 nearest neighbors, right? Or any number of neighbors, really. And since the algorithm we're going to be using is the same, right? Count the number of neighbors and compare, right? We're going to replace the specific number, 3 or 5 or 7, with just the letter k to stand in as any integer value, right? So what we've just come up with is called k nearest neighbors, or KNN, right? So k, that value, 3 or 5 or 7 or 51 or 100 million and 1, right, is what we call a hyperparameter, which means it's a decision that we need to make before this model can be run, right? It can't learn the value of k. We have to tell it the value of k, right? So speaking of training, speaking of learning, right, you might have noticed that our model didn't train at all. We started with a bunch of plotted data on 2 axes, and KNN just jumped in and started making predictions based on the values already assigned in the data, right? So KNN gets lumped in with other machine learning algorithms, even though it doesn't have that iterative training process, right? And the expression we use to explain that away is that the data is the training, right? The process of labeling this data, right, is sort of the training process of KNN, right? It just uses the straight data to make predictions. It doesn't really have to fit itself, right? So maybe it's not a perfect fit for the philosophy of machine learning, but it's still a pretty useful model. So the last model we're going to be using today, in addition to our decision tree and our KNN, is called a support vector machine, or SVM. Right? And so the SVM is a little bit more complicated than the other 2 models that we've seen so far, but our focus right now is just how to use it in Python, not actually on the math that's going to drive the performance of this machine, right, this model. So for right now, we're just going to say that SVM learns a decision boundary between classes of data, right? And that's a term that you should remember from video 3, by maximizing the index in the data, right? And the index is this distances between instances of data and our decision boundary, right? So to maximize it means to make it as great as possible. But how are we going to put all of these little distances together, right? Is it a sum, or is it an average, or is it the sum of the squares of each of these different distances, right? That's another hyperparameter that's going to get chosen when we write our code. And as a matter of fact, SVMs have a lot more hyperparameters than the other 2 models we've talked about so far. Fortunately, SciKitLearn is pretty good at choosing default parameters for us. So for today, we're not going to worry about tweaking these parameters. We're going to mostly use the defaults provided by SciKitLearn so that we can focus on the actual process of training this model and making predictions with it. So these three models are classics of machine learning and have been used for decades now. But they're mostly replaced now by neural models, right? Models based off of neurons. So, of the three, the SVM is still the most useful, although there are definitely still applications for KNN and decision trees, right? And that's okay though, because today we're going to be learning some useful Python, right? And it's a great way to start talking about the train test pipeline for our models, right? How are we going to get our data? How are we going to divide our data so that it's useful as a train set and a test set, right? And how do we make predictions after we've trained our models? All right, so now that we've laid that groundwork, we're ready to start writing some actual code here. I encourage all of you to be in front of an IDE so that you can code along with me, right? And this is VS Code that I've got set up right here. The first thing I'm going to write in this file is the most important part of any coding project, the comments, right? So first I'm going to name myself as the author of this file, right? We could even like name the channel here. And you can see I've already got the name of the video up there, right? And so now down here, I'm going to start sketching out everything that we're going to need to do in this file, right? It's super important to understand the logic and the flow, right, and the structure of the code before you start writing any code, right? Or else you're just going to get lost in there, right? You're going to write yourself into a corner. You're going to forget your algorithm, right? You're going to write confusing code. So, big picture, what are we going to do, right? I know we're going to do some imports, and then we're going to have to get our data set. And we're going to have to train our model. Right? And I know we have 3 models that we're going to look at today. But right, let's just start looking at one, right? Right? And then we need to test our model on different data, right? That's an important thing in machine learning, is that we need to keep our train and test data separate so that we can see the actual performance of our model and make sure that it is generalized well, right? That it's actually learned the patterns in the data. So I've put imports up here first, even though that's not really required in in Python, right? And there are 2 reasons for that. First is that I learned C and C++ before Python, and this is just kind of a leftover habit from those languages. Second, Python programs run until they hit an issue, right? Which means if something goes wrong down here in our code, right, it's going to run this line and then this line and then this line and then this line first, right? So all of that's going to happen before we hit that line down there. And if I'm missing a dependency, which is just an expression for external code that our program needs to work, I want to know that right away. I would rather Python, right, throw an exception right here and say, hey, I don't have that library. So I know that we need 2 libraries for this program, right? We need SciKitLearn, which is the import name of the SciKitLearn library, and we need NumPy, right? And this gives us a cool opportunity to look at a couple of tools in Python, right? So the first we're going to learn is the as keyword, right? Python lets us give nicknames to libraries that we import frequently, right? So, that we use frequently in a program. So here, NumPy, right? If I don't want to type NumPy every time I use a tool from the NumPy library, right, I could nickname it something much shorter. So like NP is an extremely common one, right? But we should ask ourselves what happens, right, if the code for these libraries isn't on my computer, right? And we can fix that down here if that comes up. This is a terminal. VS Code gives us a little terminal to work in here. Right? So if I was missing a dependency, I could jump down here and install, for instance, NumPy. Right? Pip is a package management tool for Python. Right? So I've asked it to install NumPy for me, and it's telling me requirement is already satisfied, right? Because I know I already have that library installed. So now, SciKitLearn, the next library we're going to need to import here, is a big library, right? Like big. And we're only going to use a few tools from it. So instead of importing the whole thing, right, we're going to learn another keyword today, the from keyword, right? So instead of grabbing the whole library, I'm just going to grab a little chunk of it. So for instance, from SciKitLearn.neighbors, I'm going to import the kneighbors classifier, right? And from SciKitLearn.tree, I'm going to import the decision tree classifier, right? And from SciKitLearn.svm, and you can see VS Code is helping me complete these names, right? So if I down, and then tab, it'll fill in that SVM for me. I want to import SVC, right? You might ask, why is this SVC and not SVM, right? You should remember from video 3 that there are 3 main tasks we can do in machine learning, right? Classification, regression, and clustering. And it turns out support vector machines can do more than one of those. So we specifically want the classifier from the support vector machine module of SciKitLearn today. So I'm just getting the classifier. So these 3 lines give us access to classes that were implemented in the SciKitLearn library. These 3 classes encapsulate, right, which means kind of wrap up a lot of work that is required to train and test these 3 different models, right? So even though they all train differently, every object created from one of these 3 classes is going to have a method called train and another one called predict, right? That's one of the cool things about object orientation, is that it lets us hide complicated tasks like training a machine learning model behind a simple interface, right? Like our .train method or our .predict method. So now we also want our data set, right? And we're also going to get that from SciKitLearn. SciKitLearn supports some common, what they call toy data sets, right? Simple data sets that are easy to work with. So we're also going to need to get our importer for the data set, right? So that's going to come from SciKitLearn. You could probably guess this one, .datasets, right? I'm going to import load wine, right? We are working with the wine data set today, right? Because that's just a fun thing to talk about, right? Wine and booze, always cool to talk about. All right, so, and something you might notice here is that VS Code has colored this differently, right? Because load wine is not a class like these other 3 imports are, right? Load wine is a function, right? We got one particular function out of this file. So I don't need any class or function definitions, right? We don't need to define our own custom functions for any of this, right? So I just want to go ahead and start working in the main portion of my program, right? Which I'm going to put under this if statement, right? For reasons that we talked about way back in like video, I think it was 1 when we first started talking about this stuff. So if name is equal to main, right? So down here is where the rest of our program is going to go, right? So like we were talking about a second ago, right? Load wine is a function, so I'm going to create variables named x and y, and I'm going to use those to catch the return of the load wine function. And I'm going to start working under this comment, right? Because we have actually started working on the useful portion of our program, right? That's one of the nice things about SciKitLearn, is that you can jump into it extremely quickly. So I've created variables named x and y, right? Remember that in Python, we create variables just by assigning a value to them. I'm going to call loadWine. I'm going to set return xy, which is a keyword argument. I'm going to set that to true so that x and y get returned separately rather than as just one data set, right? Because it's easier for us to work with them like that today. Yeah, and I think that is all of the arguments we need to pass in to this function, right? Just this one keyword argument, return xy, right? And so now normally I would say one-letter variable names are a bad practice, but x and y are kind of a convention in machine learning, right? It is very, very normal to refer to your data as x, right? And you can subscript it. We'll see that a little bit later on if you want to split up your train and test data, right? And y as your labels, right? So big X is our data and little y is our labels or our targets, right? You might have heard either one of those terms before. So let's think about this data for a second and compare it to what we saw in the doodles we were looking at earlier. I want to train my model on some chunk of data, right? That means some portion of this variable x, which is going to be a list of values, right? But I also want to save some of that data so that I can evaluate my model later on, right? I need my test data as well. That's how we're going to see whether or not our model did a good job of fitting itself to the data, right? So fortunately, SciKitLearn has a built-in tool for splitting your data into train and test sets, right? The name of that function is train test split, unsurprisingly, right? And we're going to get that from SciKitLearn.model selection. We will import train test split. Awesome, right? It's yellow again, right? We can see that that's another function. And if we're splitting the data, right, the x values, we also need to split the y values that go along with them. And that's a nice thing about using this function is that it's going to split the data and the labels in the same place, and it can still do that randomly, right? But it'll still make sure that the train data lines up with the train labels and the test data lines up with the test labels, right? So I need to pass x and y. Whoop, sorry. Train test split, we pass it x and y, right? And I'm going to use the test size keyword argument to decide how much of the data gets used to train the model and how much is held out to test it later on, right? So really you want to reserve as much data as possible to make sure that your model learned a good generalized relationship, right? So good performance on a very small test set might just be an accident, right? That could be a coincidence. And likewise, bad performance on a very small test set might be a coincidence, an accident, right? So 70% train, 30% test, or 80% train, 20% test are pretty normal. However, I know that the data set we're using today is really small. It's only 178 instances of data. So I'm going to use a 90-10 split, right? That's 90% train, 10% test, to make sure that our model has enough data left to train itself, right? So that means setting test size to 0.1, right, or 10%. And I want a random split, so I'm going to set the shuffle keyword argument to true. That's TRUE with a capital T, right? That's another funny thing about Python is you have to capitalize true and false. But I want you all to be able to get the same results as me if you run this code. So I'm also going to hard code random state to be 42, right? I'm going to set the random seed to be fixed so that even though this split is random, it will always be the same random split, right? And that sounds a little bit weird, but remember that computers are pseudo-random rather than true random, right? So randomness doesn't always behave for them like it would for like you or I. Okay, so x and y both get split. So our two inputs will make four outputs, right? So notice right here I'm calling this function, but I'm not catching its return yet, right? So I'm going to need four new variables to catch the return of our function, right? Xtrain, xtest, ytrain, and ytest, right? I'm going to use my assignment operator, right, to take everything that comes out of this function and put it into these variables, right, which will also create these variables for us. Now, let's give ourselves a decision tree classifier and start training it, right? It's just that fast with SciKitLearn, right? We are 3 lines of actual code into our main function, and we're ready to create our classifier, right? So we've already imported that from SciKitLearn up here. So I just need to catch the return of its constructor in a variable that I'm going to call model, right? So remember that a constructor is a special function, right, that belongs to a class whose job is to create an instance of that class, right? It's loading in some values and stuff for us. Okay, so I'm going to catch its constructor by calling decision tree classifier, right? A constructor is a function, so I run it with parentheses. And I'm going to use the criterion keyword argument, right? And I'm going to set it to entropy. Right, I'm going to set it to entropy so that this model will behave the way we just discussed in the doodles, right? And looking at this, that actually needs to be a string. There we go. Right, we discussed that machine learning models can have hyperparameters, right? So criterion is one of those hyperparameters, right? We're telling it make the splits between branches using, right, the information entropy. So every model in SciKitLearn has a fit method. So we're just going to call that and pass it our training data and our training labels. That's all that takes, right? So model.fit, right? And you can see VS Code is auto-completing this for me because, right, it knows the data type of model already, right? Because we just created model on an earlier line of this program. So our train data is xtrain. Our train labels are ytrain, right? And now, if we call model.predict, we're saying, hey, take the relationship that you've learned with the train data, right? And now apply that relationship, right? Apply your observations about patterns in that data to some different data. We're going to get back predicted labels for every instance of our test data, right? So here's where I'm going to pass in xtest, right? This function is going to return a value. So I'm going to catch that value in a new variable that I'm going to call ypred, right? Short for y predicted, right? So these are the labels that our model thinks should belong to the test data. And if our model worked very, very well, ypred and ytest will have the same list, right? So let's print them and see if that's what's happened. All right, so we will print ypred. Let's print ytest first, and then let's print ypred. There we go. All right. If we come over here, we should be able to run this data or this program, which is indeed a Python file. right? And it looks like they're pretty close, right? So our first instance of test data is supposed to be a 0. We predicted a 0. Supposed to be a 0. Supposed to be we predicted a 0, right? Supposed to be a 2. We predicted a 1, and then 0, 0, 1, 1, right? It's close, but it's not perfect. And also, it would be nice to see these predictions in a more interpretable format, right? Instead of having to compare value by value, could we get like a nice summary, right? So we're going to produce what's called a confusion matrix, right? Which is a summary of exactly, right, what values were assigned to the test instances of data and what values were predicted by our model for those test instances of data, right? So we're going to import that from SciKlearn.metrics. We're going to import confusion matrix. There we go. Yeah, I didn't remember exactly how that function name was written, but right, VS Code knows for me. All right, so this is going to be a matrix, right? A matrix is like a two-dimensional table of numbers, right? And the rows of this matrix will be the correct labels. The columns of this matrix are going to be the predicted labels, right? So the top left value of this matrix is going to be, for instance, like assigned 0 and predicted 0, right? So let's see what this looks like. Confusion matrix. What do we need to pass it, right? We need y. All right. So I'm calling this function with 2 arguments, right? First is the correct labels. Next is the predicted labels, right? And I'm going to print this so that we can see it in our terminal down here when we run our program again. So here we go, right? So the top left value here tells us that 7 instances of data had the assigned label 0, right? And that label corresponds to some varietal of grapes, right? And of those 7 instances of data, right, 7 of them were given the label 0 by our model, right? So we correctly labeled every instance of data that has the label 0, right? But if we look at this column, right, that tells us 8 labels were predicted by our model to be a 0, right? But only 7 of them were actually labeled 0. And so now kind of similarly with row 1, column 1, so here that middle value, right, we see that 7 instances of data have the label 1, and 7 instances of data were predicted to have 9 total instances of data were predicted to have the label 1, right? So we correctly labeled every instance that did have a 1, right? But then we also overpredicted, right? And so on this last row, right, that's telling us that the model was wrong a few times, right? There are a few instances of data. There are 3 instances of data that were supposed to have the label 2, but our model said, right, 2 of them are label 1 and 1 of them is label 0. To summarize that, what do we see here, right? These diagonal values here tell us how many times our model was correct, and everything off of the diagonal is when our model was incorrect, right? So if we want to compute the accuracy of our decision tree, all we have to do is add up all of the correct values, that's the diagonal of this matrix, then divide by the total number of guesses that were made, right? So that's the sum of all values in the matrix. So if we guess 10 times and we find that 8 of them are right, that is 80% accuracy. So let's write an operation to compute the accuracy of our model, right? So the comparison operator equals is going to return a list of Boolean values if we compare ytest and ypred. And I'm trying to keep them in the same order as the function call up here. Right? So if we compare a list to a list, the return is going to be a list of true or false values, right? True when they match and false when they don't, right? And if we count the non-zero values in that list, right, which I'm going to use a NumPy function called count. There it is. Right, so if I use count non-zero on this list, right, what I'm going to get back is the number of times that two values from this list did match, right? Because falses will be cast to the integer value 0 in this comparison, right? So then we'd have to divide by the total size of our matrix, right? Which we can get using the len function, right? So the left side of our division here is going to be the total number of times we were right. The right side of our division here is going to be the total number of guesses that we made. So this division is going to return the accuracy of our model. Right? I'm going to put that in a print statement so that we can see it. I'm going to label that print statement with just the word accuracy, so it's a little bit less confusing, right? And if we give this a run, right, we've still got our confusion matrix here. We're still printing that, and we can see that our model was about 83% accurate. Now, this operation is a little too long and a little confusing to just be sitting there inside of a print statement, right? I would want to explain this operation with a comment, right? So, accuracy, right? Which, like, a savvy reader should also be able to notice the label in this print statement, right? Or even better, I could take this little line of code and move it up into a definition to compute the accuracy of a prediction. But fortunately, SciKlearn already has a function that's going to tell us the accuracy of our model, right? And a lot more with that. So I'm going to grab from SciKlearn another function called classification report that is also from SciKlearn.metrics, which means that right, I can import multiple things from this one library at the same time. I just separate them with a comma. And now we can get rid of this operation inside of our print statement here, and instead just call classification report with ytest and ypredicted, ypred. So if I run this, right, we've still got our confusion matrix here, and everything below it is the report on the performance of our classifier, right? So here we have our accuracy is 83%, right? And there's a lot of other values here, right? We get a lot of other different measures like precision and recall and F1, right? And we see the support for every class, right? We're going to talk a little bit more about these other metrics, other ways of measuring the performance of a machine learning model in a later video. So for right now, let's just focus on the accuracy, and we see it is 83%, right? So this is telling us that SciKlearn is getting the same result as our little NumPy operation that we wrote ourselves earlier, right? So it's always nice to have that kind of validation, right? And to see that a piece of code we wrote agrees with, right, a piece of code in an established module. All right, so our accuracy is 83%, right? That's pretty good, right? Is that the best we can do, right? Is decision tree classifier the best classifier, right? So adding our KNN classifier should be pretty easy, right? We call the constructor, we call fit, we call predict, right? We catch the return of prediction into ypred, we print its confusion matrix, and then we print the classification report, right? And then we're going to do all of that with the SVM, right? But here's the problem. I don't want to rewrite all of this code, right? And all this stuff, right? It would keep going and keep going, right? Code duplication is actually a pretty bad design choice because it makes your code more difficult to maintain. Any change that we make to this code would have to be made 3 times over, right? It makes your code more difficult to read, right? Because understanding one block of code, right? And then still requires reading 2 more blocks of code to see that, oh, look, they do the exact same thing, right? And it also makes it easier to accidentally add bugs to your code, right? If I'm retyping all of this code over and over again, or even if I'm copying and pasting it and making small alterations, there's always a chance I'm going to goof something in there, right? So I'm going to make a little proposal. Let's make a list of our machine learning models that I'm going to call models, right? Remember that in Python, lists are enclosed in square brackets like this. And then we'll just grab one model at a time out of our list, store it into a local variable down here that we can call model, right? And then we can use all of this same code to train and test each model, right? Maybe like in a loop that's going to run 3 times. Right? But we only have to write the code once, and then we'll let it run however many times we need it to run. So I'm going to give you a few seconds of silence here to pause the video and try making those changes for yourself, right? Or if you're not in front of your IDE right now, just try to think of how you would make those changes, right? And then when you are in front of your computer, you can circle back and try typing them out yourself. All right, so pause the video, take a few seconds to work. Okay, here we go. Our models list contains a decision tree, a KNN classifier, and an SVM, right? And I went ahead and set the number of neighbors for KNN to 3 using the nNeighbors keyword argument, right? So really now we could call this 3NN, right? 3 nearest neighbors, right? And notice that now all of the individual model objects don't have names in this list specifically, right? They're part of a named collection. The list is named models, but every object in this list is nameless, right? It's not referenced by a specific variable. And that's okay because our for loop down here gives them a local name as it iterates over the list. Every model gets pulled out of the list, which is named models, right? One at a time, it's given the local name model, right? And then, right down here in the body of this for loop, model refers to whichever object we pulled out of our list, right? So we can use the interface, the shared interface of each of these classes, right, to fit our model and then predict some values, right, and then test our predictions, right? And that works because every model has the same interface. They're instantiated from 3 different classes, but SciKlearn wrote the same interface for every classifier class. right? So consistent and intuitive interfaces are good design. So, thank you, SciKitLearn. So running our code will give us a confusion matrix and a classification report for each of the three classifiers, right? I'm also going to print the type of the model here with some little dashes thrown in to separate them, just to give us a better understanding of which results are being printed, right, on each iteration of this loop, right? And this isn't necessarily the best solution, right? Using the type function, it would probably be better to make this a dictionary instead of a list, right? But for now, this is kind of the quick and dirty solution. This is the smaller solution for right now. So reading over our results, right, we can see in the classification reports that here, decision tree did 83%. 3 nearest neighbors, right, or KNN with a neighbor's value of 3 did 83%, right? And here, the SVM, right, with no keyword arguments, this is just your bog standard basic SVM, only did 78% accuracy, right? It performed worse than the other two models, even though it's a much more powerful classifier. And that's actually a pretty good lesson, right? For simple problems, right? And this is a pretty simple data set. Simple machine learning algorithms, right? Simple classifiers often do better, right? So the older models we're looking at today might be less popular than more powerful, more recent neural models, right? Real cool stuff like LSTMs and CNNs and ResNets and whatever else, right? But these older models are still useful on the correct problems, right? Simple problems like this. And that's actually going to wrap it up for this video. I hope you had fun. I hope you learned a lot. I'm always open to feedback, so please don't hesitate to leave a comment below if you have any requests for future videos, or just hit the like button if you want to say, hey, keep going how you're going. Subscribe if you want to catch the next video in about 2 weeks, when we're going to start talking about our first neural models. See y'all in the next one.